Well, with no further ado, I'm going to dive right into the training. I'm actually going to dive right into the training. I'm going to review what we have gone through or what we did in the previous class. That was yesterday class. Yesterday, the 12th of March, AD 2021. I'm going to go over a quick run of what we did yesterday. So I'm going to share my screen. All right, and we did gray direct PV sizing. That's what we've been talking about. Gray direct PV sizing, sizing the system, um, system sizing, and we identify limits to PV system sizings. There are a lot of factors that comprises of limitations. A lot of factors that affects how large a system can be or how small a system can be. We calculate the PV array sizing using our online PV wax tools. Apply appropriate system loss factors. We did. We created a chart for our location to help us in the sizing. And we went on to determine the correct numbers of PV model for a given applications. So we went further to we have done system according to annual electricity consumptions, and then we did system sizing according to space, roof space, available space. So we did system sizing based on available space and system sizing based on annual electricity consumption. Today I'm going to run over system sizing based on budget. Budget in the sense how much the customer is willing to spend, how much money the customer is willing to spend. If you have a customer to tell you, well, the only money I have to do this project is $2,000, then you should be able to tell the customer how much of a system they can get for $2,000. As a company, we have our price per watts. Now, when it comes to sizing per budget, what is done is that the manufacturing, the installation company, that's us, factor into consideration the price of the PV model, that is your solar panel, the installation cost, material costs, all other relevant costs associated with getting a system installed, and they divide that cost by watts. So, for example, a company can tell you, and if you want us to size a system based on your budget, it's $2 per watt. So if a company tells you that system size is $2 per watt, that means that they have already factored into consideration they need inverter, they need charge controller, they need all of your wiring, they know all of that, they factor all of that and divide that by watts, individual watts. So let me go further. Let me go further. I'm going to run through all of these. No need to go back over that. We did it already. Let's proceed. Let's move forward because we have another material to dive in today. Some budget. Sizing example based on roof. We did that. Sizing of roof. Sizing example based on budget. Now, I'm going to read a little bit. This system sizing is based on the customer budget. If a customer has a maximum budget of, say, $13,000, and assuming that they could not take advantage of federal tax credit, in America, they got something called federal tax credit. When you install panels over your house, the government gives you a tax credit so that you can be, because you are helping the environment, because you are using environmental friendly electrical source, using the solar system, the sun. So you get incentives. There are incentives in developed countries. I don't know about Africa, but there are. I was told that there's duty free for solar panels in Liberia. So you get some incentives. So take advantage of the federal that they could not take advantage of the federal tax credit, and there are no state or utility rebates. And the typical installation rate for the area is $3 a watt. The system could be sized. Now, $13,000 is the budget the customer has. We divide $13,000 by the installation cost. That's what it said. Installation rate. The installation rate. Every institute have to have an installation rate. For example, we currently have a project, and that project has an installation rate. How do we determine the installation rate? The total project, say for example, the whole project is $15,000. We're going to divide that $15,000. We're going to do the math to find out how that $15,000 installation cost could be divided into a single wax. So if we have to size for a customer based on budget, we would be sizing based on a single wax. That's how they found that it costs them $3 per wax, not just the panel, because somebody would think that, oh, it's just a panel. That includes every factor that comes with having an system built. 13,000 divided by $3 a wax of the PV model, PV, equal 4,333 watts of PV. Now you divide that by 1,000, you got 4.33 kilowatts PV model. Then you multiply that by what? The area kilowatts hour per year. Now we did that using our PV watts calculator. The area kilowatts per year. Today, we're not going to be working from Liberia. We're going to assume that we got a job in Nigeria and we're taking our team to Nigeria. So we're going to be working from Nigeria today. We're going to find the area. We're going to find the geographical location. What will be the costs? I mean, what is the kilowatts hour of that geographical location? So we're going to work with Nigeria today. Now, taking in consideration this example, share that the customer budget is $13,000 divided by the cost of installation, which is $3, which is the PV watts, giving them 4.33 kilowatts PV system. We're going to multiply that by the area kilowatts hour per yearly. We find this 1,452 by using our PV watts calculator. If you were in the previous class, you understand you should be familiar with the usage of the PV watts calculator. I'm going to go back there and do it again. But this time I'm going to use all of the default values with the exception of the wax system. Now, write that down. So I'm going to say, for example, our customer, this, for example, the customer budget is $15,000. I'm going to write this, I'm still learning how to use my pad. It's called, it's like a notebook. I'm still learning how to use this bad boy. I'm still learning how to use it. So, let me see more options. Well, I'm going to use it. I'm going to use something else. So I'm going to come here and use pink. So our customer in Nigeria, we're going to say location, Nigeria. Customer will be uh, we say Peter Brown. Customer name is Peter Brown. Customer budget. Customer budget. Customer budget. Customer budget is $15,000. That's our customer budget. Location is Lagos, Nigeria. Customer name is Peter Brown. Customer budget is 15 grand. We have to find kilowatts hour for that geographic location using our PV watts calculator. So we're going to come here. Use the PV watt calculator to find PV watts. We went through it. You know what PV watts is. The PV watt calculator. To find area kilowatts hour yearly. All right. Using the PV watt calculator to find location kilowatts hour yearly. So we're going to use find location and the kilowatts hour. So we're going to go to our PV watts calculator. All right. Oh, hmm. System size based on budget. I think if I write like that, will look better. Let's see. Hold on, I'm also going to improve on my using my material. system size based on budget. Right. So our Google's is open. Just that. Go in there to the PPWise calculator. PPY calculator. We are looking for kilowatts hour yearly for Nigeria. So we say now you notice that we said Nigeria, but they give us what? They give the solar resource data. They give us the latitude, the resource data information for Ghana. That is because the closest area to Nigeria that it has data for is Ghana. If you look on the map, they're using the NREL International Data Weather Data, and we have Lagos. So we are not wrong. So it's Lagos. So it's the same geographical area. We're gonna find. So we come in here. DC system size. You know this. We change this to 1. System model type. We say 1. We say standard. Array. We change the array to what? Roof mount. Fixed roof mount. We're going to leave the system losses the same. We're going to click over here and we change the sorting to 3 and we change the shading to 10. That would 10 to 21.9. I don't want to change the sorting because we don't have much sorting in Africa. So I'm going to leave that to 2 because we don't have much sorting. You don't have a lot of snow and stuff going on the roof. Shading, you don't have much shading and stuff. So I will leave this to 2. I'll just leave it by the default. I'll leave it at a default. I'll reset it back to the default. Some default. Shading 3. Alright, we're gonna just stick with that. So angle everything here, I'm gonna leave it the same. We're doing a residential. I'm gonna click over here that says go to PVY result. I click over here, I click on this arrow. What's it over here? This arrow. So the kilowatts hour yearly for a geographical for based on the weather data for Nigeria is 1,413 dollars. 13, not $13, 13 kilowatts hour kilowatts hour here. That is our result. That's the information we need. If you look here, they even tell you the solar radiation right here. Solar radiation daily. Energy, the AC energy kilowatts, tell you that daily right here. So that's what we have. We don't know the money, we don't know how much is our utility in Nigeria. So what we need is this information right here. Now we're going to go back to our material. According to our material here, we have to use the budget, the available budget of the customer, which is 15 grand. The customer budget, I wrote down, customer budget is 15 grand. $15,000, that's the budget of the customer. Now our rate for our company is $2 a watt. So $2 a watt. So we're going to come back here and I'm going to clear this here. I'm sure you could copy it here. So you write it down. Clear this here. All right. So we will bring back. Remember, write down the formula. Budget divided by watts. Price of our watts. Get the answer of how many watts. and then we divide that into kilowatts. Divide that into kilowatts. And then we multiply the kilowatts by the kilowatts. Multiply that by the kilowatt hour of the geographic location. I'm gonna write that down for you. Budget divide by installation watts. Price of installation watts, you can say. For us, is $2. And that will give us our watts PV. Divide that by 1000 to get our kilowatts. Our kilowatts, we multiply our kilowatts by the location, kilowatts hour year. Right. So I'm going to practicalize that for you. And we come here. What is a budget? The customer budget is 15 grand budget. Mm-mm. Budget is 15 grand. All right. And price, the cost, the price of watts, the cost instead of I would say uh, installation is $2. Installation watt cost is $2. Installation watt cost is $2. Mm-hmm. And we have to find the watts PV, which comes and we have to find the kilowatts, and so forth. So what was that? For Nigeria, we already have the kilowatts hour year for Nigeria. So that's what we're gonna do. So now we're gonna say 15 grand divide also do a division sign. Oh no, come on. I'm trying to learn how to use this pen. Technology got its own pros and cons, man. I know it. 15 grand divide by what? Cost installation watt cost, which is $2. All right. Installation watt cost is $2. All right. Just say 15 grand divided by 2.00. So the customer PV watts, customer equals customer PV watts will be 7,500 watts. 7,500 watts. Then click on it. 7,500 watts is a custom PV watt, custom watts PV. You have to use the appropriate terminologies. All right, now we have to change this here to kilowatts. To find this, to change it to kilowatts, all you have to do is divide 7,500 by 1,000, which will give you 7.5. Well, let me just do it for mathematical purpose, divide by 1 gram. So you have kilowatts is 7.5 kilowatts. 7.5 kilowatts multiplied by the location kilowatts hour of 1,413. So times 1413 equals 10,597.5 watts. Now we divide that by 1,000 to get our kilowatts. So your system size will be what? 10.6, because after the 5, the next is the 10th place. So we'll do what? So your system size, custom system size, (10.6 kilowatts). That's a custom system size. That's the system size, 10.6 kilowatts. Customer budget is 15 grand. The installation watt cost is $2. We take the 15 grand, we divide by the installation watt cost of $2. We have what? 7,500 watts. That's a PV watts. We divide that by 1,000 to give us 7.5 kilowatts, which we will multiply by the location kilowatts hour year, which will be 1,413. Multiply by 7.5 multiplied by 1,413 would give us 10,597.5. We have to break that down into kilowatts, which will give us 10.6 kilowatts. That would be the size for that customer at 15 grand. The customer tell you, I have 15 grand, that would be the size of the PV system. So that size is, I have to raise the cost a little bit for us because that size is too high for that budget. So we're going to do a little bit raising. We're going to raise out a little bit. So it's going to be 3.00, so 15,000 divided by $3 equals this, divided by 1,000. 15,000 divided by $3.00, divided by 1,000, 5 kilowatts. 5 kilowatts times 1,413. So the system will be 7.0, 7.1. So, not a fraction though. 10 kilowatts. 7.1. That's 10 times 7.1% equals 0.71. 10 minus 0.7. All right. So our installation costs is too low. We have to work on our installation cost based on budgeting in Liberia. That installation cost is too low. So installation cost, we're going to raise our installation cost $3, considering the fact that we have to include all other installation material, mounting and everything else. So that installation cost is too low. So we're going to change that to $3.50. So we're going to change that to $3.50. So let's do that. Come back here, 15,000. Oh no, I don't want you. So we say 15,000 divided by 3.50 $3.50. So we have a system sizing of 4,285.7, right? 4,285.7 divided by 1,000. We have 4.3. I'm going to run the number off. So we have 4.3 kilowatts. 4.3 kilowatts multiplied by 1,400 location kilowatts hour year, 1,413. So this is 4.3 times 1,413 equals system size would be 16,000. 16,007.5.9. Divide that by 1 gram. Our answer will be 6.1. 6.1 kilowatt system at 15 grand. So right there we know what is our installation cost. Our installation cost is $3.50 a watt. Doesn't matter what solar panel you use, that's the installation cost for our company, $3.50. So we have customer budget is 15 grand. You're going to be able to get a 6.1 kilowatt system. Now, if the customer budget is a fraction of 15 grand, which is what? 7,500? 7,500. It's simple. If you already know that 15 grand is going to get a customer 6.1 system, 6.1 divided by 2, customer got a 3 kilowatt system, 3.1. Leave the one. It's a 3 kilowatt system. Customer going to get a 3 kilowatt system or a 6 kilowatt system. Just go by 6 kilowatt system. 3 kilowatts. So if the customer has $7,500 budget, it's a 1 kilowatts, a 3 kilowatt system. 3 kilowatt system. If the person has a $7,500 budget. So 3 kilowatt system. That includes your inverter, charge controller, the battery, and everything else. So 3 kilowatt system. So that's how it's done. That is how you budget. You size a system by budget based on the budget of the customer. Now, let's say, for example, a government institution. The government have a project. The government want us to put solar installation over a multilateral high school in Zwedru. And the budget for that project is 50 grand. The budget for that project is $50,000. That is the budget the government have for that project. Put a system in there that will handle, will provide stable electricity for the Zwedru multilateral school because they want to now revamp or re-establish the science lab and so forth. Based on the budget, we already know our price is $3.50 a wax. So the budget is 50 grand. So we come right here, customer budget. Oh man, let me just. Wow, technology. Since technology was introduced to me in the year 2002, I Sierra Leone, when I first came across computer, it have made everything in my life very, very accessible, and it has given me the opportunity to not because I have in America they tell you you have a dyslexia. In Africa, they tell you it's slow. But in America, it's just that you're not the kind of person that can think or focus on 5 things at once. Some people have problem with remembering words. Not that they cannot compose the writing, the typing they do great, but if so you have tools, and computer system have been one of the greatest tools I have used in my life. That have put me in a place where I can do a lot of tremendous things that I wouldn't have done if I was in Africa, considering the kind of educational system you have there. Hello, we're still waiting for the people to call or to set today. They will call you by the end of the day once everything is all set. Just not on the phone with them all day. All right. So we have 50 grand. The budget. So we said the $50,000 they have. I'm gonna say the budget of the government is 50 grand. Our installation cost is $3.50. So we divide that by $3.50. 50,000 divided by 3.50. We have 14,285.7. The rest you just leave it there. So that's all we have. Now we're going to divide that by 14,285.7. 285.7 divide by 1000 equals 14.2. Take a 1, so it's 14.3. So we got 14.3 kilowatt system. 14.3 kilowatt system. Our geographic location in Liberia, so we have to find the kilowatts hour year for Liberia. So we go back to our PV watts calculator. It's not Nigeria. We go to what? New location, change location to Liberia. 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 Searching the weather data for Liberia. So good. We have our longitude and latitude and longitude for Liberia. We click go. DC system sizing. We do the average. We do one, not a standard. We do standard model, fixed open rack. We do roof mount. System losses. All of that. We come here. Sorting. Maybe that area, it's this is a sorting, so it's already defaulted. The shading is 3. The sorting here is 2, so we'll leave it by default. Click OK. They don't have snow. Go here. So for Liberia, the kilowatts hour yearly is 1,535. So we write that down. 1,535. That is our kilowatts hour using the meteorological data. So we have what they call 1,000. So that's just 1,535 kilowatts hour year. That's for Liberia on the international level. That's why I tell my students, I'm training you as an international student. That's why we say here. You look behind here, it says it right there. It says it right there. Voma energy. Energy that changes lives. Our job is to change lives and improve the livelihood of our people. And so some days we can, when we are long gone, somebody can say there was one short boy here who started this whole thing. All right? One time, the greatest thing I ever heard in my life, somebody to refer to me was when, after I left the refugee camp in Sierra Leone and went down to Freetown, and after I think a year or two, I returned back to the camp. An older gentleman said to his friend, "Don't you know this boy?" I said, "No." He said, "If this young man was here, what these camp management people are doing to us, they wouldn't be doing this." So people watch you. People's eyes are on you. You don't pay people, people watch you. They see the little good you are doing. They see what you are all for. They watch you. They may not go on Facebook all the time to acknowledge what you do, but people take note. That's what the Bible said, that even God, the Bible said the Lord is writing. He writes down. Men do take notes of your actions. Nowadays, people are so much looking for authentications. Oh, people didn't comment. People didn't do this. No. People watch. They keep that record for the future. Tomorrow, somebody somewhere will say, I know somebody from the hard work and the sacrifices. So whatever you do it to your best. This is my advice to my students and all those that may be come across this training material. Now, the meteorological data record for kilowatts hour yearly for Liberia will be multiplied by 1,535. So it's 14.3 times 1,535 equals 21,950.5. Divide that by 1 gram, won't get a kilowatts. Our kilowatts will be 21.21, 1.9. So our kilowatts hour would be 22. But this is what we have. We have our answer here. So if we divide this and round it up, we divide 21,000, 21,000, 950.5. So we got 21.9. 21.9. If you take 1 from there, you put it, this is 10. So we take that 1, we put over there, so it's going to be, we're going to run it up. Now our system up to 22. It's 22 kilowatts. Our system size would be 22 kilowatts. That would be the size of that system. So for a budget of 50 grand, when we do the system sizing based on budget, which is $3.50, that is our rate, we'll be able to install a 22,000 kilowatt system in that school. A 22,000 kilowatt system. Now, 22,000 kilowatt system, do you know how much solar panel is that? I'll tell you right now. Students should know that. 22,000 and 22 kilowatt system, 22 times 1,000. So you got 22,000. If you choose what model you want to use, you want to use 325 watts model. That's 68 PV model if you run it out. 68. If you run it out, 68 PV model. So if you use 325 watts PV model, we have 68 models. 68 pieces of PV model. That's what you have. 68 pieces of PV model. That's what you need. 68 pieces of PV model. Now, I'm going to use a system. I'm going to use a software to design that system. Watch me. So we know our system size, 22 kilowatts. That's our system size. Now, that's the importance of non-understanding computers, but programs. I want to use a system that will tell me what my inverter will be. It will tell me a lot of stuff that I need to know about. So we have 22 kilowatt system, 22 kilowatts. I'm going to come here. I'm going to use a software program already there. You can pay monthly to use for 90 bucks a month. If you have your design company, it's called Hello Scopes. Beautiful, beautiful program. If you want to do system designs. Ooh, your account have expired. They need me to pay money. I don't like. I like to use the. I like to use. I like to use free version. Log in with. This one is bad. Just look at this one. Alright, so I use a lot of so okay, for example, yeah, they're not gonna let me do that. Want me to pay that money? I'm gonna pay that money. I'm gonna log out and see. So this is how much time I've actually used this program. Format corporation, yeah. I'll use all of these addresses. Use that system. They will not let me. I don't want to pay money. Hmm. Well, never mind. It is gonna take a lot to do that. But I wanted to go through to show you how you can design a system there for that. To tell other things about inverter and other things, but we'll do that later. We'll have to use a different email to create a new trial version. I don't pay for those things. I just use them trial. That's what I do. I use them trial. I just use them trial. All right. So let's move on. Let's move on. So now we have already gone through discussing system sizing based on budget. So that's what we have just done. System sizing based on budget. That's what we have just done. System sizing. We did annual consumption already. The array watts divided by the model watts equals number of models. That's what we just did. Array was a watt. So we had 22,000 watts. We divided by the model watts. So whatever model you want to use. You want to use a 60 cells or a 72 cells. Whatever model you want to use, whether you want to use a 290 watts or you want to use a 345 watts model, that is up to you to choose what models best will save you a lot of space. If you don't have a lot of space, you have to use higher watts model. Same thing, just make it easier. Use higher watts model. PV array sizing summary. What are the possible limit to PV system sizing? What are some variables you may have to adjust in PV watts to determine the production of a PV array? PV system sizing may be limited by what? Usable space on the roof or the ground. Customer budget. Customer electrical usage. Utilities often have a cap of the size of the system they will allow based on the customer previous 12 months of electricity consumption. We did that. Impose limits by utility or sometimes in developed countries, the utility company tell you you can't just offset all of your 100% of your utility current from your solar panel installation. They just how much you can offset. Maybe they tell you can only offset 50%, or you can offset 70%. You can just say, I don't want a utility now. I'm going to do my PV. Some countries they have restrictions. You can't do that. PV array production will vary based on numerous different factors. Some of those can be the adjusted those can be adjusted in PV watts, including system location, type of model, type of mounting array, tail angles, array azimuth, detailed system losses can also be adjusted, including soiling, shading, snow, model mismatch, wiring, system age, several other factors. We can also enter in the specific DC to AC power ratio. So all of these has to do with system sizing. So that is the end of this chapter, this course. Not a course. This chapter of our course. Redirect sizing using that's our course we were doing as a current course sizing, redirect sizing. So that's the end of that one. I was thinking about doing another course. All right, let's run through this tab. Now, grade direct sizing considerations. There are some considerations, some factors to consider when sizing a system, grade direct sizing. The grade direct sizing consideration. Demonstrate how temperature impact PV voltage. Describe why temperature is an important system design consideration. Describe DC to AC power ratios and how it applies to system design. Explain when to use a higher or low DC to AC power ratio. The learning objectives for this lesson are to demonstrate how temperature impacts PV voltage, describe why temperature is an important system design consideration, describe DC to AC power ratios and how it applies to system design, explain when to use a higher or lower DC to AC power ratios. The gray direct sizing consideration, seasonal PV model array voltage. They happen to allow PV models regardless of what type of power electronics they are connected to. The maximum inverter DC voltage, seasonal PV voltage, the minimum inverter MPPT voltage. Now the coldest day, the volt. So they show these lines here as we go along on the graph. Blue stands for the voltage average. This purple stands for voltage winter. Yellow stands for voltage summer. So as we go along, that's what they're trying to show you, that we're going to see these colors on the graph showing us the voltage average, the voltage winter, and the voltage summer. Now, if you look right here, a PV system designer has a lot to consider when deciding how to optimize a system for a location. Since PV system production is dynamic and based on weather conditions, the PV voltage need to be evaluated at the high and low temperature for a location to make sure it fits within the inverter or the MLPE operating parameters. Inverter manufacturers provide the maximum system voltage limit. The top red dot line, which must not be exceeded, because this could damage the unit and may void the inverter warranty. The highest the PV model and array voltage occur during the winter when the PV model open socket voltage VOC reaches its peak in cool early morning before cell temperature start to rise with the sun and before the inverter even turn on. This is shown on the graph with the purple line, and the maximum volt VOC is the blue dot. The model VOC temperature coefficients of volt VOC and local temperature data can be used to determine the highest number of models in series allowed when staying under the maximum system voltage limit during the coldest temperature of the year. This is a very important aspect of PV system design. If you live in cold weather temperature, if you are designing in cold weather areas, these are very high factors to take in consideration. We don't have these constraints in Africa more, like Liberia, we don't. You will not experience a very cold temperature below 0 degree. I don't even think it get as cold as 30 degree in Liberia. I don't think so. Maybe you get some cold air in December. You get what we call the Yanipepe period. Inverter manufacturer also state the minimum MPPT voltage limit, which is the lowest voltage an array can operate at while tracking the maximum power point of the array. Shown at the bottom red dot line on the graph. The lowest PV model and array voltage happen during the summer, when PV model maximum power voltage VMP SAC during hot temperatures and full sun in early afternoon. While the PV system is operating, this calculated using the model VMP and the temperature coefficient of the power. TKP PMP stands for power. To determine the minimum number of models in series that are required to stay above the inverter minimum operating voltage during the hottest time of the year. This is very important. When you are building a system, the inverter is very important. The inverter job is to change your DC current that comes from your PV model into an AC current, as we said in the early lessons. But taking into consideration, there are a lot of factors that affects the full operation of an inverter. Power factors are very important, and as a designer, you have to take these into consideration. If not, you're going to damage an inverter that costs hundreds, if not thousands of dollars. The great direct sizing consideration: cells temperature, the IV curve, and the MPPT windows. The inverter MPPT range 2,500 to 2,000, 250 to 550 volt. That is the MPPT, the maximum power point tracking. That's what MPPT is. Maximum power point tracking. The maximum power point tracking of this inverter is between 250 volt to 550 volt. You cannot excel that. You cannot even go close to 550. You have to stay below the maximum, stay within that bracket. The array maximum point. What is the array? The array is a PV model, the solar panel. Those are your arrays. That's why they're showing that. The array maximum power point. 1,000 watts, they have that. They have array maximum. This is very important. You want to look at your PV model. It will tell you the maximum power point of it on the label behind the PV model. It tells you, or if you look at the data sheet of the PV, every manufacturer has a data sheet. If you check the data sheet of your PV model, it tells you the maximum power point, MPPT, maximum power point of that model. Inverter operate at reduced current. Inverter unable to operate entire IV curve outside its voltage window. It won't be able to operate outside its voltage window. The volt is 2,250 volt to 550 volt. You have to be able to have models that support 2,550 volt. You cannot have model that cannot. That will be the inverter will be operating outside the IV curve, and that will not work. It will not function. Will not even work. Inverter maximum voltage equals 600 volt. That's what they're saying here. Now let's read something about it. This diagram shows how the maximum power point MPP of an array shift with temperature and why it is so critical to design an array where the VPM on the hottest day of the year stay within the MPPT operating range of the inverter. The inverter is able to track the MPP of the array within the operating voltage windows. In this case, 250 volt to 200 to 550 volt, until the model cell's temperature reaches 50 degrees Celsius. At this temperature, the low array VPM means the inverter is no longer able to operate at the MPP, the maximum power point. The inverter is forced to move along the IV curve to a high voltage closer to VOC and lower current, and the array power output is significantly reduced. The inverter cannot track the actual MPP of the array at 55 degrees Celsius, 55 degrees, that's 55 degrees, because the MPP voltage is lower than the inverter maximum operating voltage. This is very seasonal, very important. When you are configuring your inverter to work with your model, your PV model, or your PV array, the PV array are group of PV model. PV model are commonly known as solar panel. When you take two or more solar panels and combine them together in series, you call, or parallel, you call those arrayed. So it's not called, you can say group of solar panels, it's called arrayed. That is the right terminology for it. So we're talking about the highest temperature and the lowest temperature. Actually, the array temperature heats up to 65 degrees, at which point even the VOC of the array will be less than the minimum possible operating voltage of the inverter, and the inverter must shut off. PV system designer need to calculate the array VMP at the highest expected temperature for the number of models in series. Make sure that the number, make sure that the number is within the MPPT window of the inverter. If not, even if the inverter does not shut off completely, a lot of energy production can be lost, as shown in this example. Very important to take into consideration. You have to take into consideration. So you're going to read the installation manual. You're going to read the data sheet. You have to read the information. The installation manual will tell you how much of a series, how much model you can put in the series, and the model will tell you how the informations are given. It's like you buy a bed from a furniture store. It comes with a manual showing you how to assemble that bed. If you don't follow the manual, you will spend more time there, and if not, you may not even assemble that bed the right way. That's why the manuals come with it, the installation manuals. So model's temperature coefficients. The model temperature coefficient. 1 second, guys. Read this right here. I'll be right back. The model temperature coefficient. All right. Patient. Now, model temperature coefficients. TK. PMP. Tell you right there. That is right on the data sheet. The information right there is given. Or maybe right on the nameplate behind the solar panel. These information are given. For instance, you will see it right here. The power. There's a 290 watts PV model at 60 cells. The IMP is 8.9 and the VPM is 32.64. 8.9 amps, 32.64. The TKPM is negative 0.50% of a percent's divided by the degree. So if this model is 300, is 35 right here. If this model is 35 degree, 10 degrees Celsius, 10 degree hotter than STC, it will lose 5.0% of its power VPM. If this model is negative 50, negative 5 degree, 30 degrees Celsius colder than STC, its volt can be 10% more than its STC. So it's important to check or read the installation manuals, these information when installing, when pairing, when uh, installing your PV system. Model manufacturer provide temperature coefficients so that system designer can calculate the change in voltage, power, and current due to changing PV cells temperatures. For each model, there is a minimum and maximum number that can be wired in series for a given location in order to stay within the string inverter voltage window. Temperature coefficients are typically provided for VOC, RSC, and PMP. They are most commonly represented as a percentage change per degree of temperature change. For example, percent divided by degree. But they can also be given as a unit per degree of temperature change. For example, volt divided by degree Celsius. The example of this slide shows the coefficient for voltage, TKVOC, and power TKPMP are negative, since voltage and power will decrease as the cell's temperature rises. Straining sizing calculators or longhand calculations will help a designer ensure that the PV array is configured so that the open circuit voltage VOC of a strain of models does not exceed the inverter's maximum voltage limit during cold temperature, and that the minimum number of models in series is enough so that the VPM will stay above the minimum inverter MPPT voltage during the hottest day of the year. SEI has provided a string size calculator spreadsheet as part of this system sizing lesson. You see how beautiful this institution is? Where we get our material from? They have provided a calculator we can use for string sizing. What is the DC to AC power ratio? Great direct sizing consideration. DC to AC power ratio. We have a 6 kilowatts PV array STC right there. And we have a 6 kilowatts rig inverter. The PV DC watts STC is 6 kilowatts DC array. Divide by the inverter AC ratio is 6 kilowatts AC inverter. The DC to AC power ratio is 1 ratio. That's a DC to AC power ratio. If you have a 7.5 kilowatts DC array and you have a 6 kilowatts PV inverter, AC inverter, you divide the 7.5 kilowatt DC array by the 6 kilowatts AC inverter, you have a 1.2 ratio. That's your AC to power, your DC to AC power ratios. If you have a 3 watts DC model, divide by 250 watts AC macro inverter, you have a 1.2 ratio. Very important. The DC to AC power ratio describes the relationship between the DC array input power to the AC output power of an inverter. This express using the STC ratings of the PV array and the nameplate AC ratings of the inverter. When determining the power ratio, the inverter nameplate AC power ratings is always used, and the variable will be the DC array size. It is common to see PV array with a DC watts rating that is higher than the inverter AC watts rating. This is because most PV array rarely operate at or above the standard test conditions, STC. That's what STC is, standard test conditions. Irradiance is often lower than 1000 WM, 1000 watts, m to the m squared. And when irradiance is high, cell temperature are likely to be hotter than 25 degrees Celsius. Low irradiance and hot sensor temperature means the power output of an array is normally lower than the STC wattage. This means that an insignificant amount of energy is lost when an array DC rating is slightly higher than the inverter AC rating. Got it? They are saying if your PV model array, the DC rating is slightly higher than the inverter AC rating, you lose. That is an insignificant amount of energy is lost. That is an insignificant amount of energy is lost when an array DC rating is slightly higher than the inverter AC rating. Insignificant. I mean, not important. For example, a 7.5 kilowatts DC array divided by a 6 kilowatt nameplate inverter ratings equals 1.25 DC to AC power ratios. A ratio of 1.1 to 1.2 is reasonable for many residential systems. A typical array is 1.10 to 1.4. The PV watts default value is 1.2. Some large-scale systems have ratios as high as 1.50 or possibly higher. Some other terms you may hear that describe this relationship include array to inverter power ratios, DC to AC ratios, DC load ratios, oversize ratios, overload ratios, or inverter load ratios. These you may hear. Great direct size consideration. Why is it important? 5,000 watts inverter. Inverter maximum output power. Extra power productions. It's a staple shoulder. So you see, they're showing that you have a 5,000 watts inverter, 5,000 watts inverter maximum. The high DC to AC power ratios, the low DC to AC power ratio. Look at the graph. It shows you during the peak of the sun, 7 a.m. in the morning, you don't have no peak. Going up to the afternoon hour, you are the higher peak of your rate. And then it start coming down all the way to 5 p.m. It come back down. So 7 a.m. the sun start going up. By noon is when you have the best of your sun. That's why this is the time if you have washing machines and those things, and when you use those equipments, washing machine, you want to wash your laundry, your clothes, do that in the peak time, 12 p.m. between 12 and 1, 2, do that. That's time. Do all of your high consumption, use all your high consumption electrical appliances. So to enjoy them. Then the sun start coming down at 5 p.m. The sun goes down. Power clips losses. Low ratio below 1.1. Little to no power clips, especially in especially in hot, low elevations, climates. High ratio about 1.3. More overall power production, more PV model. As these are things to take in consideration. More overall power production, more PV model. Assuming ratio does not get too high, more power clips. especially in cold climate or high elevations. The black bell curve is called the black bell curve. Line represents a DC to AC power ratio of 1. When the DC array watts equal the AC inverter output watts, the origin, the orange belt curve, the orange bell curve. This is the orange. The orange bell curve is higher DC to AC power ratio. The extra usable power generated by a large array or higher ratio is shown in yellow and is typically available in the morning and the afternoon. So you see the yellow here, very a lot, and it go down. High extra power production, get more power. That's why commercial businesses and so that operates in the day, got machinery and things to operate, use them in the day. Don't use it at night because at night you're going to use a battery bank. Around midday, if the PV array DC power exceed the inverter's AC power ratings, the inverter will limit the output power to its nameplate ratings, which is commonly known as the power clips, shown in blue. When power clips, the inverter increases the DC operating voltage, which shifts the array operating point away from the maximum power point on the IV curve to limit the power output of the array. At hot, low elevation climates, the long summer day typically increases cell's temperature, especially on roof-mounted systems, which reduces the array output power and the likelihood of power clips. Array located at higher elevation, high irradiance, and in cold climate, low cell temperature generally experience more power clips with a high DC to AC power ratios. Very important to take into consideration. Note the bell curves shown on this page represent a full sun ideal day. Reason reason to choose a high power ratio. Submotinium site conditions. Shading, array tie, and orientations. Hot locations reduces installation cost. Inexpensive PV module fixed costs, driven by incentives or interconnections. Limit AC kilowatts but not DC kilowatts. Shoulder capturing of peak optimization. Increase productions, inverter run at higher full capacity for more time per day. It's a 8 kilowatts PV array with 6 kilowatts rated inverter. There can be quite a bit of additional energy harvested by oversizing an array. With careful consideration given to the number of factors include local climate data, local irradiance, incentives, and cost PV model. So, okay, you want to get an incentive the government is giving, so you increase your PV model. That's what it's saying. Some of the factors in developed countries, not places like Africa. Government are giving incentives for installing panels over your home. So there are situations where a higher power ratio make a lot of sense, including climates that are hot, smoggy, hazy, or dusty year-round, as well as shaded locations. These locations are unlikely to see standard testing conditions. Okay, we don't have much standard testing condition. Nobody's going to go to your house to check to see what you do, but you want to do your best. It's important to stand up the international level or do your best to get close to proficient, to be proficient and adequate with what you're doing. 1.5 atmosphere, very often, so minimum power clips is expected. When PV models are expensive, it can financially be financially beneficial to add more models so that during the early and later time of the day when irradiance is lower, the larger array will allow the inverter to operate at full power for longer period of time. Some incentives programs or utility interconnection agreement limits the AC system size, total kilowatts of connected inverter, but not the DC system size, total kilowatts of PV array, providing another potential motivation to increase the DC to AC power ratio. High DC to AC power ratio can allow the system owner to capture high value kilowatt hour rates, such as on peak pricing by increasing system energy production during peak hours. Is there a limit to how high a power ratio can be chose? Yes. Be aware that too high of a ratio can lead to more DC current than the inverter has been designed to handle, which can damage or destroy an inverter. So always stay within the inverter manufacturer limit. Another important factor to keep in mind is that the larger the power ratio causes the inverter to work harder and run hotter for longer hours, which may lead to decreasing service life if it occurs frequently on a recurring basis. If you train the inverter with a lot of PV models, adding more models than the inverter can handle, or it will affect the inverter. That's what they're saying. Take that into consideration. Reason to choose a low power ratio. High elevation, cold climate. Places that have high elevation and cold climate, you want to choose a low AC to power ratio, low ratios. Inverter optimization or manufacturer limit. Customer performance. Some inverters are more efficient at low capacity. Different may be minimum 6.6 kilowatts to 6 is. Some project location will not gain much from a higher power ratio. Areas which are higher in elevation has a thinner atmosphere and higher irradiance, which will cause the PV array to operate closer to or sometimes even higher than 8 STC ratings. Additionally, snow is reflective and can cause the array to have a higher output. For these reasons, system is smoothing. Location may benefit from low power ratios. Some inverters operate better at low power ratios, so it is always important to refer to the manufacturer instructions. Additionally, customers may have a limit budget, and low DC to AC power ratio tend to have low upfront cost. Small PV arrays, some customers hate seeing any power clips on their system, feeling that they are paying for power that they are wasting. It can be important to educate the customer about the system performance, hence to manage expectations. At this time, I'm going to close up right here and we'll continue with this course in our next class. It's been a great day, a great training section. Thank you. Look forward to our next class.